Hello guys, in this video tutorial I would like to explain about the purely random process. Initially I will explain the concept, what is meant by purely random process, and then I will try to explain this in R. We'll try to simulate from the purely random process and then plot the data, the purely random process data and their autocorrelation function. We already have some graphs from the books, so we will try to validate those results, and we will try to validate those results which we have in theory and mathematical equation and statistical equations. Uh, in the earlier lecture before this, I talked about stochastic process and then about the stationarity of a time series and the importance of stationarity of time series. Um, the description, the link to that lecture is given in the description of this video, so you can see that video. Okay, so let's move to the theoretical concept of the purely random process. Uh, Purely random process, a discrete time process, is called a purely random process if it consists of a sequence of random variable zt. Let's suppose zt is a random variable which are mutually independent and identically distributed. So this means that these zt variables are IID, independently and identically distributed. We normally further assume that the random variables are normally distributed with mean 0 and variance sigma square z. Okay, so this is further assumption that these variables are normally distributed with 0 mean and variance sigma square z. From the definition, it follows that the process has constant mean and variance. So mean 0 is mean, that is constant, and sigma square z, that is constant. Moreover, the independence assumptions means that, okay, so independence assumption means that if we calculate the correlation, the covariance function at lag k, this means at lag k, this is equal to covariance of, between zt and zt plus k. So this means that zt and zt with the k lag, this is equal to, there are two possibilities, that is equal to sigma square z if k equal to 0. Let's suppose k equal to 0 in this here, then this is the covariance between zt and zt because k is equal to 0. And remember that when you are calculating the covariance, this means you are calculating the covariance, the variation of the two variable zt and zt plus k. But if k equal to 0, this means that both variable are same, zt and zt. Then the covariance become the variance of the zt, and we already stated that in the assumptions that the variance is sigma square z. So if k equal to 0, this means that at lag 0, zt and zt, then that is equal to the variance, that is equal to sigma square z for lag k equal to 0. And this covariance is 0, covariance function is 0 for all other values of k. K may be plus 1, minus 1, plus 2, minus 2, and so on, because we already stated in the assumption that this is independently and identically distributed. So it is independent, therefore the covariance function is 0 for all legs other than leg 0. I mean no legs. So this from here you can calculate the correlation coefficient, which is equal to 1 if k equal to 0. This is equal to 1. I mean, I will explain this because this is covariance, and remember that the variance of the correlation between two variable is equal to the covariance in the denominator and standard deviation of x multiplied by standard deviation of y if we have two variable. So in this case, we will have covariance for this correlation coefficient. We will have a formula which is equal to covariance between these two variables divided by standard deviation of zt divided by standard deviation of zt plus k. But remember that here k equal to 0. This means that lag is 0. So in the numerator there is variance. Of course, this will convert to variance sigma square z. In the denominator, this has a standard deviation sigma z, and this has standard deviation sigma z. because both are zt at like k equal to 0. So in the numerator there is sigma square z, and the denominator there is sigma z, which becomes sigma square z, and therefore this is equal to 1. So the correlation coefficient at, I mean, if you are using no legs, that is equal to 1, and the correlation coefficient for all values at all legs at k equal to plus minus 1 plus minus 2, that is equal to 0, because the covariance is 0 and the denominator is 0. So whatever is in the denominator, this will be 0. So you can deduce this result from here. You should know the correlation coefficient formula, and then you can deduce this result. So this is all about the purely random process, theoretical concept, that what is meant by that. And now let's move to our study, that how we can do. This is something that we have an example, and you can see that this is the original data of the purely random process which generated from normal distribution, and this is then the autocorrelation function which we explained in the previous slide. You can see this is the autocorrelation function, the autocovariance function, and the autocorrelation, the correlation. So this is 1 at leg 0 and 0 at all other legs. And so you can see here that at leg 0 this is 1, this is autocorrelation function, and all other values lies between the two blue lines, which are the 95% confidence interval. So there is no line outside these two lines, there is no spike outside this line. This means that these spikes are not significant, and you can consider it's approximately 0. So this is 1 and all other are 0, and this is just the interpretation of this equation by this graph. Now let's do this in OR, that how we can do this in OR, how we can simulate, and then how we can plot these two plots in OR. Let's move to OR. So let's suppose that we need to draw 500 observation as we did in the slides. So this is just I fixed the number of observation, that is 5. Now z, just assign a variable z, which was zt in the text, but we don't need to write this subscript t. Okay, you can, but for simplicity I'm just writing z, and this is r n o r, and this means that draw random number, simulate random number from normal distribution, that is n, which is 500 in the first step, 500 observation. You can directly write here 500, it's no worry. And then this is 0 with the 0 mean, and variance 1, suppose variance 1. Okay, so this is also, let's run this and then run this, and you can see in the slide what is the next. Okay, now I need to divide the screen into two parts. This command will partition the graph, this screen into two parts. I would like to explain this. This command will divide the screen into two parts. This means two rows and one column. If you write 2 instead of 1 and 1 instead of 2, then there will be one row and two columns. So just take care. The first one is for rows and the second one is for columns. And this is margin. You can choose margin, mean you can increase or decrease the margin for from the four sides of the graph, and there are four parameters. Just do this, and now let's plot the data, the upper graph, the series. I mean the original data, just plot like this graph. Okay, let's do this. Okay, you can see this graph. Okay, let's make it bigger. Okay, so this means that I'm just plotting z, which is the variable which has 500 values with 0 mean and 1 variance from normal distribution. Type is L, mean that the graph is line, the type is line. Xlab is time, which should be here, and ylab is series. Now, and x time is not mentioned because I just cut it more, the margin, because then the graphs will be very thin. So but you can put 4 here and here, then you will see the time. Now I need to draw the autocorrelation function which is mentioned in the slide like this. Let's do this. Okay, now run this. Yeah, okay, you can see the same result which is in the book, in the slides like this. So this is the series and this is the autocorrelation function and this is the interpretation of this purely random process in R. You just transform this in the software R Studio so you can do, and this is up to you. You can plot. This is for generally for leg 25, but you can increase the number of legs. That is lag equal to 50. So I can increase this for legs until leg 50 and 100 and so on. Suppose I will draw the same graph for the series, this, and then you can increase this to 100 legs, whatever you like. So this is look like this. I don't like this because this is very congested and multi. I think you can draw until 25 legs or 20 legs. That is enough. Okay. Okay, so this is about all about parallel random process, the concept, theoretical concept, and how we can do this in our studio. I hope this will help you. You like this. In the next video, I will talk about random walk model, and then I will move slowly and gradually to AR model, MA model, and then to ARIMA model, Marx Jenkins methodology. Uh, if you like the content, please subscribe the channel and see you in the next video. Ciao.